Hi everyone, today a video in the transition metals and inorganic reactions set of videos looking at inorganic reactions and colours. So the first thing to start thinking about when we think about these inorganic reactions is actually the acid-base chemistry of our aqueous ions. So we said in the very first video of this series that if we dissolve a transition metal salt in water, for example if we take iron sulfate, FeSO4, that water molecules cluster around the metal cation. And so we don't think of it existing just as Fe2 plus and the SO4 2- ions, but actually as our hexaaqua ion, our hexaaqua complex ion of our FeH2O6 2 plus, and then also our sulfate anions there to balance that charge. But the key thing that we're really concerned about is that metal ion. We're considering the water molecules clustering around that cation, and so we have our hexaaqua ions, not just Fe2 plus on its own. And so the way that these water molecules bind, we talked about again in the first video, is these ligands use a lone pair to form a coordinate or a dative covalent bond with the metal. And so we have this dative bond where we have both electrons, not a shared one and one electron kind of normal covalent bond, but both electrons coming from the water molecule. And you can see there that I've shown an example of this coordinate bond with the water molecule making a coordinate bond to a proton, an H plus ion, and this creates our oxonium ion, the H3O plus ion. And remember that if we have an acid in solution, that acids never go around as H plus, they're always coordinated to a water molecule to make H3O plus. But that's an example of our coordinate dative covalent bond. Now what we actually say is that our metal is a Lewis acid and the ligands are Lewis bases. And so we already probably know the definitions of the Bronsted-Lowry acids and bases, that a Bronsted-Lowry acid is a proton donor, our Bronsted-Lowry bases are proton acceptors, but we can also think about the Lewis acid and base definitions. That is that a Lewis acid is an electron pair acceptor, a Lewis base is an electron pair donor. And so because we have our ligands donating their lone pairs, in the case of the iron hexaaqua ion, we have our water ligands acting as the Lewis bases, donating the electron pairs, and we have our iron accepting our electron pairs, and therefore it's the Lewis acid. Now interestingly, there's actually a big difference in the acidity between the +2 and the +3 hexaaqua complexes. So all that's changed here is an iron 2 plus ion or an iron 3 plus ion, but there's a big difference in how acidic these complexes are. The iron 3 plus aqua ion is much more acidic, and the reason for this is because it has a much higher charge density of the Fe3 plus ion compared to the Fe2 plus. If we think about Fe3 plus versus Fe2 plus, well obviously we have a higher charge, 3 plus versus a 2 plus, but it also has a smaller ionic radius. You can think about the fact that as we get to higher charges on our ions, we pull our electrons closer in to that more positively charged nucleus. And so the Fe3 plus is both smaller and has a higher charge than the Fe2 plus, and therefore we say that it has a higher charge density or a higher sort of charge to size ratio. Now what this means actually is that we increase the polarizing power of our metal atom. And so what this means essentially is that we can attract electrons from the water molecules more strongly. By being more polarizing, we are kind of distorting the electron cloud, pulling the electron cloud towards the ion more strongly. So we have our lone pair, essentially don't think of them as our actual kind of sort of discrete electrons as particles, but as the kind of electron clouds, the charge clouds. We can think of these charge clouds being quite easily distorted, and they're actually more easily distorted from iron 3 plus than they are from iron 2 plus. Now what this actually means is you can think of your electron density kind of being a little bit the opposite to electronegativity. In this case we have our iron atom sort of pulling the electron density, attracting the electrons from the water molecule towards it. And it does this more strongly than the 2 plus ion does. And so by pulling the electrons away from the oxygen, it also actually pulls the electrons away from that OH bond. And so it makes that OH bond weaker. By making the OH bond weaker, the loss of a proton, the loss of H plus, is much more easy. The breaking of that OH bond to produce our O minus, essentially an OH, breaking of that H2O to make an OH and an H plus is much more easier because we have a much more polarizing ion, Fe3 plus, higher charge density, much more polarizing, and therefore weaker OH bonds. And so general rule for this kind of thing is that if you have a +3 metal ion, it's much more acidic than a +2 metal ion because it's more polarizing because of the higher charge density. And so if I take a base and I add it to a 3+ metal aqua complex, a hexaaqua complex, the base will remove the protons in a series of steps. So these happen stepwise. So we take our hexaaqua complex at the top here, the H2O6, 3+ ion, that's aqueous. We take a base, which we can just represent kind of by a generic OH-, and this removes one of the protons from one of those coordinated water molecules. We release water, essentially, we make H2O, and then we essentially we have to make sure that our atoms balance, and these equations here are very easy to make sure that the atoms don't balance, so you have to really take care in writing them. What we end up with is metal, H2O5 now, OH. So we've now essentially just taken one of the protons off the water, so we have 5 water molecules unchanged, one of them now that's an OH group rather than an OH2 group, essentially. And we also have to think about our charge. Charge has to balance on both sides. We have a 3+ ion and the -1 charge from the base, and so therefore overall the charge is 2+. So the resulting ion that we make on the right-hand side, the products, is a 2+ ion. Now this keeps on going. We take that H2O5OH ion, take more base, it removes another proton from one of those water molecules, and so we now end up with MH2O4OH2, and now a positive, just a 1 positive ion. And again, it happens a third time, but the key thing for this third time is that we start off with our aqueous ion, our aqueous base, and we end up actually producing a precipitate, our solid metal with 3 water molecules and 3 OH groups attached. So essentially what has happened here is we've had 3 equivalents of base remove 3 protons from 6 of those water molecules. 3 of them have been left unchanged. 3 of them have had a proton removed, so we've formed 3 molecules of water, and we now have 3 H2Os still coordinated, 3 OHs. And that's a solid, it's a precipitate. Now a similar thing happens with an M2+ ion. Our base removes these protons stepwise, so we go from the H2O6 2+ ion to the H2O5OH 1+ ion, and we lose a molecule of water. And then the second step happens again, and the key thing on this step is, again, we actually produce a precipitate this time. So we have this H2O5OH reacting with base, pulling off one of those protons, and we end up with our solid precipitate of MH2O4OH2. And that's a solid. Now notice how these precipitates, these insoluble precipitates, are the neutral hydroxides. They're not ions, they are the neutral species. And this is the general rule, that typically your charged species tend to be aqueous. Typically, if you have a neutral molecule or a neutral compound, that it tends to be a precipitate, it tends to be a solid. And so you can think really of a 3+ ion, the kind of hydroxide of that would be MOH3, but because we're thinking about these being dissolved in water, we also have our water molecules clustering around, so we actually have MH2O3OH3. And so that's, sometimes you'll see things written down just as MOH3 as the precipitate. But you have to remember that actually in aqueous solution that will be MH2O3OH3. And likewise for a 2+ ion, you can imagine the neutral hydroxide being MOH2, 2 lots of the OH groups. And so therefore this thinking about it being dissolved in water and our water molecules clustering around these ions, around these atoms, the metal atoms, we have our MH2O4OH2. And again, sometimes you might just see that being written down as MOH2, but remember that really it's MH2O4OH2. So the general rule, a neutral complex tends to be a precipitate, solid. Charged complexes tend to be aqueous, dissolved. Now ammonia, of course, can act as a ligand. We've discussed this in the previous videos, but it can also act as a base. And so ammonia has the same effect as hydroxide ions. So sometimes you can write your equations using ammonia as a base. And here you can see it has exactly the same effect. We can write it here, rather than writing these reactions as stepwise, which can be a bit laborious, we write it just as one reaction. Essentially, to create it, you've added all together, each individual step, you've added it together. All of the intermediate species cancel out, and your overall reaction would be your hexaaqua ion, your 3+ hexaaqua ion, aqueous, reacting with 3 lots of ammonia. Those ammonia molecules pick up a proton from some of those water molecules that are coordinated. So you create 3 ammonium ions, 3 NH4+, and you end up with our neutral complex that is a precipitate, our MH2O3OH3. And so ammonia has the same effect of these OH- ions in removing a proton because it acts as a base. Now, this greater acidity of the 3+ ions versus the 2+ ions, because of the higher charge density and the more polarizing power, explains why iron 3 carbonate does not exist, but iron 2 carbonate does. Now, the carbonate anions, again, as well as being a ligand essentially, are also a base. And so they're able to remove protons from the hexaaqua ion to form the insoluble neutral FeOH3. So for our 3+ ion, because our 3+ ion is so much more acidic than our 2+ ion is, we get this acid-base chemistry happening. We get the base that is the carbonate, removing these protons from our hexaaqua ion complex, and it produces our neutral insoluble precipitate of the Fe. Technically what it would be is FeH2O3OH3. We can often shortcut it and just write it down as FeOH3. A key thing here is that in doing this, essentially we have the standard type of reaction where we have acid plus metal carbonate gives us carbon dioxide being given off. If we think about a normal kind of reaction, we have acid plus metal carbonate giving you salt, water, and carbon dioxide. And this is exactly what we see. So we have the key thing to see is that we have our 3+ ions giving off carbon dioxide, effervescence. And that this doesn't happen with Fe2+ ions. Because the Fe2+ ions are far less acidic, and so the carbonate ions actually act as ligands, therefore they do a ligand substitution reaction rather than acting as a base. And so what this means is that we then end up forming the insoluble carbonate instead. So the key thing is the 3+ acts as an acid, carbonate reacts as a base. What we end up seeing is a neutral complex, the insoluble precipitate of our hydroxide. This can't happen with the Fe2+, and so the Fe2+, because it's less acidic, the carbonate anions actually act as a ligand, and a substitution reaction takes place, and we form iron carbonate. And so we can think about the kind of almost like the ionic equation for this, of having our FeH2O6, our hexaaqua ion, as the 3+ aqueous, reacting it with these carbonate anions, CO3 2-. These act as a base for the 3+ ion. They remove the protons, and so we form 3 lots of our HCO3, our hydrogen carbonate anions, and we end up forming this insoluble precipitate of our iron hydroxide, FeOH3H2O3. That's a solid. And so that's the kind of our ionic equation. If you ever write our overall equation, it looks quite similar. The key thing, though, is that we form CO2 and water. So we take 2 of those, react it with CO3 2-, our carbonate anions. It produces the insoluble hydroxide precipitate, 3 lots of carbon dioxide, and 3 lots of water. And you can see that if you essentially broke down the HCO3, you can end up making CO2 and H2O. Key thing, though, is that you see effervescence, you see the CO2 gas being given off. And we can derive that equation from the 2 following equations below. So you take your acid plus carbonate, giving you water and carbon dioxide. And then that's an equilibrium reaction technically, and so the removal of this H3O+ displaces the equilibrium below to the right. And so the equilibrium reaction that we have at the bottom there, by using up some of the acid, it displaces it to the right. It's an application of Le Chatelier's principle. The equilibrium shifts to oppose the change. That bottom equation, if we use up the acid by reacting it with the carbonate anions, the equilibrium shifts right to make more of that acid, and at the same time makes more of the insoluble iron hydroxide. And then for the 2+ ion, we said that we have a ligand substitution reaction occurring. It's not an acid-base reaction. We just get our carbonate anion replacing the water molecules. And so we have our FeH2O6, our hexaaqua ion, the 2+ ion this time, reacting with our carbonate anion, and this simply produces the insoluble iron carbonate, FeCO3, and we kick off our 6 water molecules. And so the key rule, again, another sort of general rule here, is that carbonates of 2+ transition metal ions exist, for example, iron 2+ carbonate, but the 3+ ions, for example, the iron 3+, iron 3 carbonate does not exist. Instead, what you get is the hydroxide produced, carbon dioxide and water, because you have an acid-base reaction rather than a ligand substitution. Now, we can then start to think about how we can distinguish our ions. So the previous slide that we saw could be a way to distinguish between if we have iron 2 or iron 3 ions. Because we know that our iron 3 ion acts as an acid, we end up producing carbon dioxide, we'd see effervescence, while Fe2 plus ion is less acidic and therefore we don't see CO2 given off, we see our carbonate being formed. Another test to distinguish between the ions is to actually add dilute alkali. So the Fe2 plus hexaaqua ion is a pale green colour. The Fe3 plus hexaaqua ion is a pale brown. Now, colour is very subjective, and actually these two pale green and pale brown colours tend to be quite similar to C. It's very difficult to tell if you have one or the other. So the actual test to properly distinguish between them is to add some dilute alkali. What this does is by adding a dilute alkali, it forces both of these to act as acids, and therefore you end up forming the actual solid neutral, the neutral complexes that are the insoluble precipitates of the hydroxides that we've been seeing. So the FeH2O4OH2 for the Fe2+, and the FeH2O3OH3 for the Fe3+ ion. So this is exactly the same type of reaction we've just seen on the previous slide. Iron is acting as our acid, the base is acting as a base, pulls a proton off those water molecules, and therefore we get water being released, and we form these OH groups. And the key thing is that they have more distinct colours. So the iron 2+ precipitate is green, quite a solid green colour, and the iron 3+ precipitate ends up being quite a strong brown colour. And so it's much more easy to tell whether you have iron 2 or iron 3. Iron 2 is green, iron 3 is brown. Another thing to talk about is something called amphoteric hydroxide. So you may have come across the word amphoteric before. Amphoteric means that it shows both acidic and basic properties. So you might have seen this if you've looked at my acids and bases videos. We've talked about the fact that water is amphoteric. It can act as an acid or a base. Another example of this amphoteric behaviour is actually using aluminium hydroxide. Now, aluminium, of course, it's not a transition metal, it's not a D block element, but it can still show this example here of amphoteric behaviour. And we're going to stick with looking at aluminium because, as we'll see a bit later on, it's useful to compare the colour of transition metals to the essential non-colour of our aluminium complexes, because it's not a transition metal, because it doesn't have part-filled d orbitals. And so aluminium hydroxide is an example. It will react with both acids and bases. And so we can take our aluminium hydroxide. Again, you could write it as just AlOH3. Of course, remember that when we dissolve these salts up in water, typically they exist as these hexaaqua ions, or at least the water molecules actually cluster around the metal ion. And so we have AlH2O3, OH3, so that's our aluminium hydroxide. React it with acid, for example HCl, and what you end up forming, very similar to what we saw in the variable oxidation states video, if we do something in acid solution, we tend to form positive ions, and so here we just form our hexaaqua aluminium 3+ ion, and we kick off 3 chloride ligands. So essentially we have our aluminium acting as a base, these OH groups on it acting as a base, picking up the proton from the HCl to make the 6 coordinated water molecules. It could also, though, act as an acid, so we now react it with some base. And like we saw in the variable oxidation states video, we have this idea that if we react these metals in alkaline solution, we typically form negative ions. And so here we form this aluminium hydroxide negative ion, AlOH4-. And so essentially what's happened here is it has picked up a OH-, if you like. Or we can think of it as kicking off 3 of the waters and picking up an OH-. And so we end up having our aluminium here actually acting as an acid. And this brings us on to ligand substitution reactions. So as we've seen in the carbonate example earlier, or we've seen in other videos of this series, we can actually replace the water molecules in these hexaaqua ions by other ligands. Now the reason this will happen is sometimes twofold. It'll either be because our coordinate bonds are stronger. We talked in, I think, the first video of this series about the fact that typically NH3 was a better ligand than water was. When we looked at hemoglobin, we looked at the fact that carbon monoxide was a better ligand than oxygen was. Essentially, if our coordinate bond is stronger, That's normally because whatever atom our lone pair of electrons is less electronegative, it's less likely to hold the electrons closer to itself, more readily donates them, the coordinate bond is stronger. Or it could simply be just because they're present in a much, much higher concentration, and so we displace our equilibrium due to the Chatelier's rule. Now, when we think about ligand substitution reactions, we can replace our water molecules by neutral ligands, like ammonia, by charged ligands, like chloride ligands or hydroxide ligands. And so it could be a complete ligand substitution. We could get rid of all the water molecules. It could be a partial substitution where we only get rid of some of them. And we can replace them with lots of different types of denticity of our ligands. Remember, denticity was how many coordinate bonds it makes. And so we have our unidentate or monodentate ligands that only make one coordinate bond. Or we can have some sort of multidentate ligand where we have more than one atom that can make a coordinate bond. And so we saw examples of our EDTA, for example, being a hexadentate ligand. It had 6 atoms on, each of them having lone pairs that can form coordinate bonds. And if we form complexes with multidentate ligands, we have this idea of them being called chelate complexes, chelation. And we saw that this was really driven in the first video of this series. The real driving force for that was an increase in entropy. Now, the replacement of water molecules will be a stepwise process. As we've seen for when we've talked about our acid-base chemistry, essentially we have this happening step by step. So the replacement of the water molecules will be a stepwise process. And so if the ligand that replaces the water molecule is also uncharged and of a similar size to the water molecule, it's likely that there'll be no change in coordination number. Remember that coordination number is our number of coordinate bonds, not the number of ligands, the number of coordinate bonds. Or there'll be no change in the actual charge of the complex if they're also uncharged. And so we can draw out these 6 stepwise reactions here. So starting from the hexaaqua ion, which is a 2+ metal ion here, reacting with a molecule of ammonia. The ammonia here doesn't act as a base, it acts as a ligand, it acts as something that's going to substitute out. And so we kick off one of the water molecules and we add on one of our NH3s. So we end up with H2O5, NH3, a 2+ complex. And so what we've done here is we've just kicked out one of the water molecules. This has been a ligand substitution. Now again, these stepwise reactions just take care in making sure that you have exactly the right number of atoms and charges balanced. They take a bit of care to write out, but essentially you can go all the way down, for example, to the very final equation here where you have MH2O NH3 5. So you've replaced 5 of the water molecules with NH3. Still a 2+ ion because it's uncharged and a similar size to the water. Add in the final NH3, that kicks off the final water. And we now we started off with a hexaaqua ion. We now have what's called a hexaamine ion here, NH3 6 2+, hexaamine ion. And so again, we can write an overall equation for this where we essentially write all of these equations together, all of the intermediate species, the things that are both on the reactants and product sides of separate reactions, cancel each other out. And when you do this, what you end up with is just the hexaaqua ion reacting with 6 NH3s to produce our hexaamine complex and kick off 6 waters. And so typically when we write these reactions, we're not going to actually write them down as stepwise. Even though they are a stepwise process, we're not going to write them down as stepwise reactions because they just take too long and they're quite laborious. We can just write it down as our overall change. But remember we said when we talked about our acid-base chemistry that ammonia also acts as a base. And so there's a few different ways that you can write these equations. If you know that it's definitely a ligand substitution reaction that's occurred and not an acid-base reaction, you can write the reaction just as that simple blue equation I've written there, hexaaqua ion reacting with 6 ammonias to produce the hexaamine complex and 6 waters. Or we can actually write it as 2 reactions that demonstrate that it acts as both a base and a ligand. And so essentially we have our ammonia acting as a base. So we can write it here as reacting with 2 lots of NH3, it's acting as a base, so it's going to take 2 protons from our water molecules. That's going to produce 2 lots of the ammonium ion, NH4+. And by taking 2 of the protons from the water molecules, we've created 2 OH groups, these hydroxide groups. And because it was a 2+ metal ion we started with, we now have this insoluble precipitate of the MOH2. So this neutral complex here, which really is MH2O4 OH2. And because it's neutral, it's a precipitate. So we end up forming our precipitate. And then typically what happens is this precipitate will redissolve. So if we add excess ammonia in, this precipitate we formed, it first acts as a base, and then because the ammonia is present in such high concentration, essentially then starts to replace these water ligands, and we get the ligand substitution. And so we have our MH2O4OH2, that precipitate, redissolving by adding it with 6 ammonias to produce this soluble hexaamine complex, kick off the 4 waters, and kick off the 2 OH minus, the hydroxide groups as well. And so it's worthwhile just double checking lots of past exam papers in your exam board to see how you can write it. Typically, either one tends to be fine. So you can, if you're told that you have this ligand substitution reaction with ammonia, you can either write it as just one equation, as shown in the blue, or as those 2 equations in black at the bottom. Essentially, you end up forming the same thing. You're either just showing it acting as a ligand straight away, or as a base first, and then a ligand afterwards. So the next type to think about is we can consider some ligand substitution reactions happening with copper. Now, when the copper hexaaqua ion reacts with ammonia, rather than the ligand replacement, the ligand substitution being full, as we saw in the previous example that we replaced all of our water molecules, all 6 water molecules were replaced by the ammonia ligands. For copper, we actually only replace 4 of the water molecules. We have a partial ligand replacement. And the reason for this is really slightly beyond A level. But what it means that we end up having is essentially our hexaaqua ion reacting with 4 molecules of ammonia, now producing this actually still an aqueous ion. It's not a neutral complex, so it's not a precipitate, it's still an aqueous ion, but it's the copper H2O2 NH3 4 2+ ion. So again, we've got no change in the charge of the complex because we have a neutral ligand. We're kicking off a neutral ligand, replacing it with a neutral ligand, so no change in charge. There's also no change in shape, really, because, as we said, the NH3 ligand is very similar in size to the H2O ligand. Now, the steps are the same as the cobalt aqua ion. First, the ammonia acts as a base. It forms this the actual precipitate of the copper hydroxide, so CuOH2 H2O4. So it forms that blue precipitate before it then redissolves. And essentially, the copper hexaaqua ion is a pale blue colour. The copper hydroxide precipitate, the neutral complex, is also a pale blue colour, but a solid rather than aqueous. And then we can write this reaction here of reacting with the 4 NH3s to produce our this copper NH3 H2O2, this partial substitution, water and the hydroxide anions, and this partial substitution product is actually a deep blue solution, so it's a darker blue solution. And so again, just double check exam boards and papers, but you should be able to write these equations either as the top kind of general equation with the ammonia acting as a ligand, or writing it as 2 equations as we saw on the previous slide, writing it first acting as a base to form the insoluble copper hydroxide, and then seeing that copper hydroxide, the light blue precipitate, dissolving back up with the ammonia acting as a ligand here to replace 4 of those water molecules. Or essentially 2 of the water molecules and 2 of the hydroxides from that precipitate, or 4 of the water molecules from the hexaaqua ion. Now, as I said, there's no change in shape really, so this is still an octahedral complex, 6 coordinate bonds, but we now actually have a distorted octahedral arrangement rather than a perfect octahedral system. For our hexaaqua ion, we have 6 water molecules because they're all the same. All of those bond lengths are exactly the same, and so we have a perfect octahedron. For this complex, we have 4 ammonia ligands and 2 water ligands. And so the shape is a distorted octahedron, and actually the copper-water bonds are longer than the copper-ammonia bonds. This is because, as we've said in previous videos, I think the ammonia ligand is a better ligand than water is. Nitrogen is less electronegative than oxygen is, therefore its electron pair is less tightly held to the atom, it's more readily donated, and therefore our nitrogen-based donor forms a stronger coordinate bond than our oxygen-based donor does. A stronger bond is a shorter bond, and so therefore our copper-water bonds are longer and weaker. The copper NH3, the copper ammonia bonds are shorter and stronger, and these water molecules actually occupy the axial position, so essentially top and bottom of our copper complex here. This is one of the reasons why this actually forms this partial substitution is to do with the fact that these water molecules are elongated and in the specific positions. But again, it's way beyond A level. If you want to look into it, it's something called a Jahn-Teller distortion. There's another type of reaction we can look at here with our ligand substitution, and it's when we react it with concentrated hydrochloric acid. Now this is quite an interesting change here because not only do we get a change of the charge of the complex, we also get a change in the coordination number and hence the shape of the complex. So our reaction is we take our blue, pale blue, copper hexaaqua ion, the 2+ ion, react it with 4 chloride anions, and the shape that we end up making is this tetrahedral copper chloride anion. So CuCl4, 4 chloride ligands around it, a 2- anion because it's copper 2+, 4 chloride anions makes a 2- charge overall, and we've kicked off 6 of the waters. So the key thing here is we've gone from an octahedral hexaaqua ion to our tetrahedral copper chloride complex. Now the reason for this, and again I think we've mentioned this in the first video of the series, is that the chloride ligands are much bigger compared to, for example, the water or the ammonia ligands. Chlorine's in period 3 as opposed to the oxygen and nitrogen for those other ligands being in period 2. And so it's a much bigger ligand, and therefore physically less of them can fit around the actual copper ion. Copper ion is quite small, it's quite towards the end of our D block. Remember that as we go across a period, things tend to get smaller because we have the increasing nuclear charge for the same quantum shell of electrons. And so because we have quite a small atom, large ligands, we end up actually having a change of coordination number, a change of shape, and so our blue octahedral hexaaqua ion becomes this tetrahedral yellow copper chloride anion. Now we can then go back to this idea of chelation. So this idea of chelation being the formation of complexes that have multidentate ligands. So the examples that we've looked at previously to this have all been complexes with monodentate or unidentate ligands, only one atom using one lone pair to form these coordinate bonds. Remember that a multidentate ligand has multiple atoms on it that can form coordinate bonds with the lone pairs. And so these complexes are usually more stable than those with monodentate ligands. The formation of these chelate complexes is favoured. The main reason is because of the increased entropy change of the reaction. And so we've seen in the first video of this series, when we looked at complex formation, a couple of examples, and I'll reiterate them here. We have our EN ligand, our ethylene diamine, or our 1,2-diaminoethane ligand, shown there at the bottom in the middle. This has 2 NH2 groups on. Both of these nitrogen atoms have lone pairs that can form coordinate bonds. So this is an example of a bidentate ligand. Each ligand molecule forms 2 coordinate bonds. This is why our coordination number is not the same as the number of ligands. We can react these EN molecules with our hexaaqua copper complex, and this produces this copper complex with 3 of these bidentate EN ligands attached. So copper EN3 as a 2+ ion. Again, this is a neutral ligand, so there's no change in charge. And actually, there's the kind of size of these ligands, it's nitrogen versus oxygen, fairly similar size, and so actually we don't end up actually having a change in shape. It's still technically an octahedral complex. And again, you can see this change in entropy here just by considering the number of moles on the left and the right-hand side. Remember that entropy is disorder, the randomness of the system. You can also think of it in terms of the number of ways we can arrange the particles in that system. All of that is increased if we have more products than we had reactants, more moles of products than we had moles of reactants. It's a more random, a more disordered system. And so you can see on the left-hand side we have 4 moles, the right-hand side we have 7 moles. So we have this increase in entropy. The other one that we talked about was the EDTA 4- anion. This was our ethylene diamine tetraacetate. And so this was our hexadentate ion, this idea that we have 6 atoms on this that are able to form coordinate bonds by donating lone pairs. So the 2 nitrogens that had a lone pair and the 4 O- atoms there that have lone pairs as well. And so this can form 6 coordinate bonds. And so we replace all of the water molecules, and potentially all we end up with is just copper EDTA. Now here we have an anionic ligand coming in, so we do have a change in the charge of the complex. It goes from being 2+ to 2-. The copper stays as the 2+ oxidation state, and so with a 4- ligand, it becomes 2- overall. And we kick off all 6 waters, and again you can see that massive increase in entropy because we go from having 2 moles to 7 moles. Huge increase in entropy. And this entropy increase is what is actually the driving force essentially for these reactions. It's what favours the formation of chelates over complexes with monodentate ligands. So it's the reason that these reactions here aren't written as equilibrium reactions, being able to go forwards and backwards, but actually just as straight arrows going towards products, because the products are so much more favoured thermodynamically because of the entropy increase over the hexaaqua ion to start with. Now, over on the right, what I've shown here is how the actual 3D structure of our metal ion, let's say the copper ion, coordinated to EDTA looks like. And you can see that it forms this quite complicated 3D shape. It's still an octahedral complex, 6 coordinate bonds. Again, it would probably be a slightly distorted octahedral complex because you have differing ligands, oxygen and nitrogen atoms. But you can see overall it's basically an octahedral complex. But actually EDTA forms optical isomers. So in the first video of this series we talked about optical isomerization. And we can see here that we actually end up forming optical isomers because we have, this is one enantiomer. You can imagine that if we had a mirror next to that and we had our mirror image form, that would be a non-superimposable mirror image. If you're not so sure about that, draw out the one, copy the diagram there and draw out the mirror image, and hopefully you'll be able to see that actually you can't superimpose these two. They're non-superimposable mirror images, and therefore they are enantiomers, the optical isomers. So they show that type of stereoisomerism. So now we're going to go through an awful lot of ligand substitution reactions of lots of the 3D transition metals. Now, just double check with your exam board exactly which metals you need to know the colours and the reactions for. I'm going to go through quite a few different metals. Just make sure that you know whether you actually need to know them or not for the exams. So the first is iron 2. Now, we said that the iron 2 hexaaqua ion was this kind of pale green colour. We can add ammonia in. Now, this can be dilute or it can be concentrated, essentially little or an excess of ammonia. And if we add it to our green iron 2 hexaaqua ion, it acts as a base and it removes protons and it forms this insoluble green precipitate of our iron hydroxide. You can see here I've written it as FeOH2. Remember that in reality it exists as FeOH2 H2O4. We have our water molecules also clustered around there. And so we can write a reaction, ammonia acting as a base. And so we have our FeH2O6, 2 plus our hexaaqua ion, reacting with 2 molecules of ammonia. They pull the protons off 2 of those water molecules to make 2 ammonium ions, NH4+. And then we form this insoluble, our neutral complex, so it's insoluble, a precipitate of FeOH2 H2O4. And this is a green precipitate. Now when hydroxide ions are added, similar reactions occur, because again the hydroxide acts as a base, and we get essentially exactly the same reaction happening, just that we're using hydroxide anions and therefore forming water. But the same ion species exist. The green hexaaqua ion, the pale green hexaaqua ion becoming this sort of slightly darker green precipitate. Now this green precipitate of our iron hydroxide, the FeOH2 H2O4, is actually soon oxidized by air. We talked in a previous video about the fact that these low oxidation state metals can often be oxidized up simply by the oxygen in air. And this happens with Fe2+ unless we protect it. And if we don't protect it, what happens is this iron hydroxide, this iron 2 hydroxide, gets oxidized to iron 3 hydroxide. So we oxidize our iron from the +2 to the +3 oxidation state, and we end up forming this now FeOH3. And iron 3+ is a brown precipitate. And so I've written a reaction here. We take essentially our iron 2 hydroxide, react it with oxygen, and we create our iron 3 hydroxide. We go through this green to brown colour change. Both precipitates, green precipitate going to a brown precipitate. And then we talked really at the start of this video about iron 2 and iron 3 in terms of the acidity and how this reacts with carbonate anions. Remember that our 2+ ions are less acidic than the 3+ ions, and so therefore if we react them with our carbonate anions, they actually act, the carbonate anions act as a ligand rather than as a base. They substitute the water molecules out, and we form this insoluble green precipitate of iron carbonate. And so FeH2O6, our hexaaqua ion, reacting with our carbonate anion to produce iron carbonate as a solid precipitate and 6 waters. And so you can see for iron 2 that generally everything is green. All of the precipitates and all of the hexaaqua ions are green. Now essentially a very similar set of reactions happen with iron 3. So we take our ammonia, either dilute or concentrated, we add it to our brown iron 3 hexaaqua ion. It acts as a base, it removes the protons from some of those coordinated water molecules, and it forms our insoluble brown precipitate of the iron hydroxide. And because it's the iron 3, the precipitate is the FeOH3H2O3. And so we can write our equation here either using ammonia acting as a base or our hydroxide ions acting as a base. And for both of them, we go from our light brown hexaaqua ion to our slightly darker brown precipitates of our hydroxides, the FeOH3H2O3. Now you can see I'm being a bit lazy with the state symbols here. I'm only showing the state symbol for the solid precipitate of the hydroxides. Just make sure you read the question carefully as to whether it requires you to put the state symbols in or not. I always make sure that I at least put the state symbol in for the precipitate to remind myself that it definitely is a solid, the precipitate. But generally most things tend to be, certainly the complexes, certainly when you add kind of the ammonia or the hydroxide in, they are aqueous. So most things are aqueous apart from these neutral complexes that are solid precipitates. And so the only difference really is the carbon anion reaction that we saw right at the start of this video. Because the Fe3+ is a much more acidic ion than Fe2+ because of its increased charge density, rather than forming the insoluble carbonate, the carbonate anions actually act as a base. They remove protons from the coordinated water molecules. They again form this same hydroxide precipitate, the FeOH3H2O3. The key thing is, though, that we see effervescence. We see CO2 gas being given off. So we form water and CO2. But again, we have the light brown hexaaqua ion becoming the slightly darker brown hydroxide precipitate. Now, I said that earlier on we'll come back to looking at aluminium. Even though it's not a transition metal, it's useful to talk about because essentially it demonstrates this idea that transition metals show colour while most main group elements do not. And so we can take ammonia, again dilute or concentrated, added to our aluminium hexaaqua ion. Now the aluminium hexaaqua ion, not being a transition metal, not having these partly filled d orbitals available to it, is colourless. And again, the ammonia acts as a base, removes the protons from the coordinated water molecules, and forms our insoluble white precipitate of aluminium hydroxide, AlOH3, or more technically, AlOH3H2O3. So that neutral complex, our solid, our precipitate of the hydroxide, and the key thing is, again, it's not a transition metal, so it doesn't show colour very readily, and so we have a colourless solution becoming a white precipitate. Now it slightly changes when we think about our hydroxide ions. If we use dilute hydroxide, or we add a little hydroxide in, we get exactly the same reaction we've been seeing for the iron species before. The hydroxide anions are acting as a base, removing protons to form this insoluble hydroxide, again the insoluble aluminium hydroxide, AlOH3H2O3, that white precipitate. However, if we add an excess of our hydroxide ions, we actually get redissolving of this precipitate. So the precipitate redissolves, and it actually forms this colourless solution of this aluminium hydroxide, AlOH4-. And we saw this when we thought about the amphoteric behaviour of our aluminium. And so again, like we saw with the ammonia, we can write this out in two separate ways. We can either write it, as shown at the top equation here, as the hexaaqua aluminium ion reacting with 4 hydroxide anions, essentially just imagining that we're adding excess hydroxide in straight away, forming this AlOH4- complex ion, the colourless solution, and kicking off the 6 waters. Or we can think about adding a little hydroxide first to form our insoluble hydroxide precipitate, and then adding excess hydroxide that will redissolve that precipitate. So we go from our insoluble hydroxide plus OH- going to this AlOH4-. So again, sometimes it's fine to write either equation. Sometimes the question might ask you to write it out assuming that you've added dilute first and then excess. So just be careful with the question. And again, here we have aluminium. It's a 3+ ion. It's a very acidic ion. And so if we add carbonate anions like we saw for the Fe3+, because of the acidity of the Al3+ ion, we see effervescent CO2 gas being given off, and the white precipitate of our aluminium hydroxide, AlOH3H2O3, because our carbonate anion acts as a base rather than a ligand, and therefore takes the protons from the water, and so you form the hydroxide precipitate, H2O and CO2 gas. So the next one then is to look at copper, and so we saw this a few slides ago, thinking about our pale blue copper hexaaqua ion. And if we take some dilute ammonia, or we have a little ammonia, the ammonia acts as a base and it removes protons from those water molecules like we've seen in all the other examples. acid-base reaction goes on, and we end up forming our insoluble pale blue precipitate of our copper hydroxide, copper OH2, H2O4. Now, if we have excess ammonia, or if we have a lot of ammonia, or even really concentrated ammonia, then this pale blue precipitate of our copper hydroxide will actually redissolve to form this sort of incomplete ligand substitution and this dark blue solution of the copper NH3,4H2O2. So we've only replaced, if we go from the starting hexaaqua ion and we add excess copper straight away, we've only substituted out 4 of those water molecules for the 4 NH3s, or we can write it as actually going from that copper hydroxide precipitate, reacting with 4 lots of ammonia, we create that copper NH3,4H2O2 complex ion, and in this case we kick out 2 waters and 2 hydroxide ions. Now, when hydroxide ions are added to the hexaaqua ion, we get again just this standard acid-base reaction, and so we end up forming again that pale blue copper hydroxide precipitate of the copper OH2 H2O4. Then if we think about carbonate anions, we know that copper is a 2+ ion, not a 3+, so it's not acidic enough to make the carbonate act as a base, and so we get this ligand substitution reaction happening. And so we go from our copper hexaaqua ion plus the carbonate anion, and we end up making this blue-green precipitate of copper carbonate and kicking out all 6 water molecules. And then finally we can think about adding chloride anions, and we saw this as our ligand substitution reaction where we had a change of the charge of the complex, a change in the coordination number, and a change of the shape of the complex. And so this is our hexaaqua ion reacting with 4 chloride ligands to make our copper chloride CuCl4 2- anion. This is a yellow solution. And the key thing is we're now tetrahedral. We've gone from octahedral to a tetrahedral shape because the chloride ligand is larger than the waters and less can physically fit around that central small copper ion. So the next one to consider here is our chromium. And we see these very familiar reactions. So if we take dilute or a little ammonia and we add this to our chromium hexaaqua ion, it's quite often written down as either being a kind of green-violet colour. I've gone for a kind of violet colour here. The ammonia acts as a base, removes those protons from the coordinated water molecules, and we form our insoluble green precipitate of chromium hydroxide, CrOH3, H2O3. If we then have excess ammonia or concentrated ammonia, this precipitate of the chromium hydroxide redissolves to form a dark green or purple or violet solution. I've gone for dark green here. Just double check with your exam board in terms of past papers what colours are actually allowed in these answers. But yeah, this precipitate will redissolve to form this chromium hexaamine complex, which is a dark green colour I've gone for here. And so again, as we've seen before, we can either write this equation as starting from the hexaaqua ion and going straight to adding sort of excess or concentrated ammonia to make our dark green hexaamine complex, or we can go from adding a little bit of ammonia first to form our chromium hydroxide precipitate, that pale green precipitate, and then adding this excess ammonia in, we get the ligand substitution kicking off 3 waters, 3 hydroxides, and creating our chromium hexaamine dark green complex ion solution. Now, when hydroxide ions are added, we get similar reactions occurring. So we have our chromium hexaaqua ion, that sort of violet solution, reacting with 3 hydroxide ions to create our insoluble green precipitate of our chromium hydroxide. If we have excess hydroxide, then the same thing as we saw occur here, we get this complete ligand substitution. This creates what we call a hexahydroxo complex. We have 6 hydroxide ligands. And so here we have our chromium hexaaqua ion reacting with 6 lots of hydroxide to create this hexahydroxo, CrOH6. Or we can write it as going from adding a little bit of hydroxide first to create our chromium hydroxide precipitate, that green precipitate, and then redissolving that in our excess hydroxide to create this hexahydroxo chromium ion again, which is this sort of dark green solution. So this hexahydroxo chromium complex, the CrOH6 3- complex ion, that dark green solution, can be further reacted with hydrogen peroxide. Now, hydrogen peroxide is an oxidizing agent, And so this oxidises the chromium 3 ion that we have in our hexahydroxo complex up to the chromium 6 ion. Now again, remember these higher oxidation states don't exist as just the sort of simple chromium ions, they exist in these sort of more complicated ions with other atoms, and so our chromium 6 actually exists in our chromate ion, the CrO4 2-, and this is a yellow colour. And so we can write our reaction here of our hexahydroxo complex reacting with hydrogen peroxide to produce this chromate ion with chromium in the +6 oxidation state, CrO4 2-, this yellow ion, this yellow solution, plus 2 hydroxide anions and 8 waters. Now this chromate ion, CrO4 2-, the yellow ion, where chromium is +6, is stable in alkaline solution. But we can convert it to the dichromate ion, Cr2O7 2-, hopefully you might recognise that as the potassium dichromate that we use to oxidise alcohols up to various carbonyl compounds. And this dichromate ion, that orange colour where chromium is +7, is stable in acid solution. And so you can convert the two by acidification. So we can write a sort of an equilibrium reaction here where we have our chromate ion, CrO4 2-, that yellow ion, reacting with some acid, because the chromate ion is stable in alkaline solution, but it will react with acid, and reacting with some acid produces the dichromate ion, this orange Cr2O7 2-, and water. And so the chromate ion is stable in alkaline solution, the dichromate ion is stable in acid solution. That's typically why we end up doing these oxidations in acid solution as well, because it's stable in acid. Now the dichromate ion can be reduced to our chromium 3 ion. This is what we see when we oxidize up an alcohol. We have to get our chromium species being reduced, and so we see the reduction of our dichromate ion, that orange coloured solution where chromium is in the +7 state, down to our green solution of chromium 3. And actually it can be even further reduced down to the chromium 2 oxidation state, which is a blue ion, by reduction with zinc. And so we can write some reactions here of our dichromate reacting with our hydrogen ions and zinc metal to produce the chromium 3, that's our green ion, with water and the zinc. And you can see the zinc here has been oxidized, it's gone from zinc metal to zinc 2+, and therefore our dichromate, the chromium, must have been reduced from +7 down to +3. And if we keep on going with this, if we have a sort of excess zinc and we allow this to carry on reacting, eventually we end up reducing it even further, and so we then end up forming the chromium 2+ ion. So we go from our chromium 3+ ion, reacting it with more zinc, and this ends up producing this blue chromium 2+ ion. Now, like in the vanadium examples that we saw earlier on, the reason why we use zinc is because we can calculate this and explain it from using our electrochemistry, using our cell potential, our E cell values essentially. And so again, if we want our chromium to be reduced, it has to have the more positive potential, half cell potential. And therefore our zinc here, if you go back to look at those half cell potentials, the zinc half cell has a very negative half cell. It's a very, very good reducing agent. It's very good at losing electrons and being oxidized. And so the reason we use zinc is because it allows the chromium to always have that more positive E cell value, and therefore its chromium is able to be reduced. So the penultimate metal here to talk about is cobalt. So we have a cobalt hexaaqua ion, this kind of pink colour, pink solution of our cobalt hexaaqua ion. If we add ammonia to that, dilute ammonia or a little ammonia, we have the standard reaction acting as a base, removing protons from those coordinated water molecules to form our insoluble blue precipitate of cobalt hydroxide, COOH2 H2O4, that sort of blue precipitate there, cobalt hydroxide. If we have excess ammonia, or we have really concentrated ammonia, then this blue precipitate of the cobalt hydroxide dissolves to end up forming our cobalt hexaamine complex, the cobalt NH3 and this is a brown solution. So we can either write it starting from the hexaaqua ion, straight away adding excess ammonia in, 6NH3, getting a complete ligand substitution, making that cobalt hexaamine ion, which is brown, and then kicking off all 6 waters. Or we can consider it starting from adding a little ammonia to make that blue precipitate of the cobalt hydroxide, and then adding 6 lots of ammonia in. This displaces the 4 waters, the 2 hydroxides, and we end up with our cobalt hexaamine complex, that brown solution. And like we saw with iron 2 being very readily oxidized to iron 3, we saw that green to brown change just in air. The same thing happens with cobalt, and so cobalt, this 2 plus cobalt ion, is oxidized by air to the 3 plus ion. So we have this hexaamine complex essentially just changing the cobalt oxidation state from 2 to 3. And this ends up becoming now a sort of yellowish solution. Now when hydroxide ions are added, similar reactions occur. So we can think about adding our hydroxide ions, taking our hexaaqua cobalt ion, that pink ion, adding our hydroxide and making that blue precipitate of our copper hydroxide, COOH2 H2O4. Now with excess hydroxide, there's no change. That's just the reaction that occurs. And so that precipitate then doesn't redissolve. We keep with that blue precipitate of the cobalt hydroxide. And this precipitate will eventually turn pink on standing. And again, it's the oxidation in air to the essentially the cobalt plus 3 oxidation state. So the cobalt hydroxide, but the cobalt plus 3 ions. So cobalt OH3 or cobalt OH3 H2O3. So essentially you'd see this, just if you left that open in air, you'd see your blue precipitate turning into a pink precipitate. And then finally we can think about it also reacting with chloride ions, so very similar to how we saw the copper ion reacting. So we take our cobalt hexaaqua ion, react it with 4 chloride ligands to make this blue solution now of cobalt chloride, CoCl4, a 2 minus complex ion. And so it's a blue solution, and again we have this idea of a change in charge and a change in the coordination number and the shape of our complex because the chloride ligand is bigger than the water ligands. Now the final metal to talk about is manganese. We see some very similar reactions here. So we take our manganese hexaaqua ion, this is a pink ion, MnH2O6 2+. And if we take ammonia, and in this case this can be concentrated or dilute in excess or a little, it doesn't matter. It acts as a base in all of these, react in all of those types of different concentrations and stuff. Acts as a base, removing protons to form our insoluble brown precipitate of the manganese hydroxide, MnOH2. And so we take our hexaaqua ion, that pink ion, react it with 2 lots of ammonia, and this produces our MnOH2 H2O4 brown precipitate. And this doesn't react further with excess ammonia, so it could be excess ammonia straight away or even concentrated ammonia. But that brown precipitate of the manganese hydroxide is oxidized by air. So we saw this with the iron 2 being oxidized up to iron 3 in air. Same thing here can happen. So the manganese 2 plus ion can be oxidized up to the manganese 3 plus ion by the air. And so you see this reaction here. Essentially all that happens is we get a slightly darker brown precipitate. So there isn't really a color change, it just goes slightly darker. So essentially you go from having MnOH2 H2O4 to having MnOH3 H2O3, so the 2 plus to the 3 plus ion. And when hydroxide ions are added, similar reactions occur. So our pink manganese hexaaqua ion reacts with hydroxide ions to produce our brown precipitate of the manganese hydroxide, MnOH2 H2O4. And again, it doesn't matter whether our hydroxide is concentrated or dilute or in excess or a little. It doesn't react with any excess hydroxide, and so we don't have any change there. But again, it will be oxidized by air and will darken to a slightly darker brown precipitate. And so again, that same reaction of the MnOH2 essentially becoming MnOH3, manganese 2 to manganese 3. And so there are quite a lot of colours to learn. Just double check with your exam board exactly what metals you need to know and exactly which reactions you need to know, because they do vary from exam board to exam board. Also check past papers, because the colours that the exam boards say on their websites and on their textbooks don't necessarily always match the colours that they want you to write down in the exams, annoyingly. So just double check the colours that are accepted in your exams. For example here, this table has been produced for if you're studying the AQA exam board. You can see that you only have to know about iron 2, iron 3, copper 2 and aluminium 3. And you can see there's a few discrepancies on here. For example, the iron 3 plus ion I said was a brown iron. Here they talk about it being a purple solution, but it may look yellow-brown. Just double check in the exam, look at past papers and see which colours they accept. Often they accept a range of colours for stuff like that. And I would recommend producing one of these tables for yourself, depending on your exam board, because it's really useful to have all of these colours and all of these actual species that exist all in one table to look at. So time to have a go at some questions here, all to do with ligand substitution reactions and essentially giving the colours of the starting and ending species. So if you'd like to have a go, pause the video and the answers will be on the next slide. So the first question here is to take copper sulfate that we're going to dissolve up in water and to add a little and then an excess separately of ammonia to that dissolved copper sulfate. So remember that when we dissolve a transition metal salt in water, what we're really considering is the hexaaqua ion, these water molecules clustering around our metal ion. So we can think of copper sulfate aqueous really as being our copper hexaaqua ion, CuH2O6 2+. Now if we add a little ammonia, we have that very standard reaction of the ammonia acting as a base, taking protons away from some of those coordinated water molecules, and therefore we end up forming a light blue precipitate of our copper hydroxide. So we take away 2 of those protons from those water molecules, we create 2 ammonium ions on the right hand side, and we end up with this light blue precipitate. We go from the blue solution of the copper hexaaqua ion, a pale blue solution, to this light blue precipitate of our insoluble copper hydroxide CuH2O4OH2, and that's a solid. Now here the question stated that they were added separately, so the way that I'm going to write my equation for using excess ammonia is to start from the hexaaqua ion again. So just be careful as to how the questions are worded. Just double check your exam board and double check some past papers to see whether you're allowed to write the equations as either one where we've either shown it dissolving up the precipitate you would initially make, or from going from the starting hexaaqua ion. Just double check some past papers and see what your exam board usually prefers. In this case, though, I'm going to start from my copper hexaaqua ion again. Now I'm going to imagine that I add excess ammonia. And so we go from having our sort of light blue solution here. And remember that when we add ammonia in excess to our copper hexaaqua ion, we get that incomplete ligand substitution. And so with the incomplete ligand substitution, we only replace 4 of those water molecules. And we create this distorted octahedral complex here, this copper NH3,4H2O2, this 2+ ion, and this is a dark blue solution. So the really key colour here is that this is a dark blue as opposed to the others that have all been lighter. Then question 2 was to look at adding both ion 2 and ion 3 to sodium carbonate, and to explain why the equations are different. So with ion 2, remember the thing we're really considering here is the acidity of the metal ion. Ion 2+ isn't acidic enough to make the carbonate anions act as a base. So instead the carbonate anions act as a ligand. We have a ligand substitution reaction going on. And so we have our ion hexaaqua ion, the FeH2O6 2+. That's a pale green solution. Reacting with our carbonate anions, kicks off the 6 water molecules, and we end up with our green precipitate of the iron carbonate. Now for the 3+ ion, we know that that's much more acidic, it's much more polarizing because we have that higher charge density. It weakens those OH bonds, therefore it makes them much more attractive to act, essentially for our carbonate anion to act as a base here and not as a ligand. And so the carbonate anions act as a base, they remove protons from those coordinated water molecules, and we end up creating our insoluble iron hydroxide, the FeH2O3OH3, that brown precipitate. So we've gone from a pale brown solution of the ion 3 hexaaqua ion to our brown precipitate here of our iron hydroxide. And then the key thing to remember is that we see effervescence. We give off CO2 gas as well. Question 3 then stated that we had aluminium sulfate reacting with a little and then excess sodium hydroxide. So remember that we take again, we're thinking about dissolving up aluminium sulfate. Essentially, we're considering the hexaaqua ion of aluminium. Now remember that aluminium is not a transition metal, so typically because it doesn't have those partially filled d orbitals, we don't see colour, and so therefore actually the aluminium hexaaqua ion is a colourless solution. If I think about reacting it with a little or a sort of dilute hydroxide, we get our hydroxide acting as the base, removing protons from those water molecules and creating our white precipitate of our insoluble aluminium hydroxide, AlOH3H2O3. Now here, the question said that we react it with a little and then excess. So not 2 separate reactions, but we react it with a little first, and then we add the excess to the same reaction mixture. So the equation I'm going to write here is actually showing the precipitate we've just made redissolving. And so we have our aluminium hydroxide, that white precipitate, the insoluble aluminium hydroxide, AlH2O3OH3, reacting now with excess hydroxide, and we know that the product with excess hydroxide ions is to make this aluminium hydroxide negative ion, the AlOH4-. And if you remember, that's a colourless solution. It's not a neutral complex, so it's a solution rather than a precipitate. And so we go from our white precipitate of the hydroxide, the Al-H2O3OH3, to our colourless solution of this AlOH4- ion. And then finally, question 4 was to write the equilibrium reaction here between EDTA4- and the calcium sulfate, and to explain why the equilibrium is displaced very far to the right. Again, remember that when we're considering, we've talked about transition metals existing as these hexaaqua ions. Other main group elements can also exist as hexaaqua ions, and so calcium, even though it's not a transition metal, also exists as a hexaaqua ion if we dissolve up a salt of calcium in water. And so you can see that it's sort of it's the element right before the 3D series, so it's maybe not so surprising that it also acts quite similarly to those 3D metals in the terms that we can get this hexaaqua ion forming. And so here we have our calcium hexaaqua ion. If we think about dissolving copper sulfate in water, what we really need to consider is our calcium sulfate in water. What we really need to consider is our calcium hexaaqua ion, CaH2O6 2+. We react this with our EDTA4-, that hexadentate ligand with our 2 nitrogen lone pairs and our 4 oxygen lone pairs. And we end up making this calcium EDTA molecule. We replace all 6 water molecules here with just 1 molecule of EDTA. We get that ligand substitution reaction. The key thing, though, is the massive increase in entropy that happens here. So we have 2 moles of reactants versus 7 moles of products. That's a huge increase in entropy. Our products are much more disordered. It's much more random. There's many more ways to arrange the product system than there is for the reactants. And therefore, because we have this huge increase in entropy, it's a massively thermodynamically favoured reaction to go towards the right, to go towards the product. And then finally here we have some more exam type questions here. And again, if you'd like to have a go, pause the video and the answers for these will be on the next slide. Answers here then to these more exam style questions. So the first one was to look at this copper nitrate and the decomposition on heating, and to give the oxidation state for the nitrogen in the various compounds here in the copper nitrate and in the NO2, and then to give what the product of the oxidation was. And so we have this copper nitrate being decomposed, essentially thermally decomposed down to copper oxide. We have copper oxide, oxygen, and NO2, nitrogen dioxide. Now if we look at our copper nitrate, the NO3- ion is a 1- ion. So if we have 2 of them, that must mean that our copper is +2. When we do redox, we always look for our most electronegative element. That's the oxygen. In this case, this has the most negative oxidation state, -2, normally for oxygen, being in group 6. And so therefore we have the 2- for the oxygen times 6 of them that there are in that formula there. That gives us -12. And so to make this overall a neutral compound, the nitrogens must be +10. And therefore, because there's 2 of them, each nitrogen has an oxidation state of +5. In the NO2, it's a bit simpler. The oxygen, again, the more electronegative, so -2. 2 lots of them, so -4. And so your nitrogen, to make it neutral overall, must be +4. And so our nitrogen has gone from +5 to +4. Therefore, it's gained electrons. Remember the mnemonic oil rig. Oxidation is loss, reduction is gain. And so therefore, we have our nitrogen being reduced. Now we then have to deduce our oxidation product, and so we can look at the copper oxide, but the copper here is still +2 and the oxygen -2. So the key thing is the copper here is +2 in the copper nitrate and +2 in the copper oxide. So our copper here actually isn't the oxidation product. But if we look at our oxygen molecule, O2, well here oxygen is a 0 oxidation state, right? It's actually existing as this molecule. So it's bonded to itself and therefore an oxidation state of 0. And the key thing, of course, is that in the reactant, the copper nitrate, the oxygen started as -2. So we've gone from -2 to 0. It must have lost 2 electrons, and therefore the oxygen has been oxidized. So oxygen is our oxidation product. Part B was taking this copper nitrate and having an excess of water. And what do we actually end up forming? If we have an excess of water, it's the same idea as dissolving essentially our copper nitrate as a transition metal salt. We know that if we dissolve a transition metal salt up in water, the water molecules cluster around the metal ion and we end up making our hexaaqua ions. So we make this copper hexaaqua ion, CuH2O6 2+, and this is an octahedral species and it's a sort of pale blue solution. Then part C was to look at adding a little NH3 to this, and we end up with this pale blue precipitate and what that is. And so if we have a little ammonia, remember that our ammonia acts as a base and therefore it removes protons from these coordinated water ligands. And so therefore we end up forming this insoluble light blue precipitate of our copper hydroxide, CuOH2 H2O4. Part D was then looking at reacting it with an excess then. So we've essentially, you have to be careful again with how the question is worded, but here we've already made this copper hydroxide from adding a little ammonia in. Now we're adding an excess of ammonia to that precipitate that we formed. So I'm going to write my equation for this. If we have an excess of ammonia with our copper, we know we form this kind of partial substitution product, our deep blue or our dark blue solution of the copper, NH3 OH2 2, so 4 ammonias, 2 waters. And so I'm going to draw this equation here actually starting from this pale blue precipitate of the hydroxide, copper OH2 H2O4. That's our precipitate, our solid, excess ammonia, 4 lots of NH3. We produce this copper, NH3 H2O2. That's a deep blue or dark blue complex ion solution. And then we've displaced 2 hydroxides and 2 waters. Part E was then looking, if we take the copper oxide, so now we take the product, and we react this with an excess of concentrated HCl. So essentially this is essentially a source of chloride anions. We know that if we've always thought about taking our copper hexaaqua ion, but the same reactivity happens if we start actually with this copper oxide, that we can essentially have an excess of chloride ligands which displace that oxygen from the copper oxide, and we end up forming our copper chloride anion, the CuCl4 2-. And remember that this is a yellow solution, and the key thing is that we have a change of charge on our complex from our starting. We think about starting from a hexaaqua ion, but we also have a change in the essentially the coordination number and the shape when we think of starting from a hexaaqua ion. And the key thing is that it's a tetrahedral molecule because physically less chloride ligands can fit around than the water ligands. Then part F, part 1, is to give the electron configuration for a copper +1 ion. Now remember that copper is one of these special electron configurations. We said that in our first video of this series that we fill using our Aufbau principle. Lowest energy orbitals fill first. We fill our orbitals singly due to Hund's rule. And so as we're doing this, what we'd expect to find is 1s2, 2s2, 2p6, 3s2, 3p6. And then remember that the 4s orbital is technically lower in energy than the 3d orbital. And so you would expect to see just for copper to have 4s2 3d9. Remember we said that copper is one of these interesting ones, in which case we shift one of our electrons, promote one of the electrons from the 4s orbital up to the 3d orbital. This is a massive increase in exchange energy, makes a more stable arrangement, and so a copper atom actually has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Now remember that while we fill our 4s, we have that slightly odd scenario that we fill our 4s electrons first, but when we ionize our metals, make ions out of them, we also lose our 4s electrons first. And so a copper plus ion just loses that 4s electron. And so the copper plus electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And then finally we have this reaction here of essentially we have copper chloride as a 2- complex ion becoming copper chloride as a 3- complex ion. Now you can see here we've not added any ligands or taken any away, it's simply the charge of that complex ion that's changed. And what that means is that it's simply just the oxidation state of our metal that's changed. So we have 4 chloride ligands in each of them, a 4- charge there. And so to be 2-, our copper must be in the 2+ oxidation state. To be 3-, our copper must be in the +1 oxidation state. And so we can simplify these equations down by removing all of our chlorines that are essentially spectator ions, and essentially have that we have copper 2+ going to copper plus. To balance the charge on that, we have to have an electron on the left-hand side, so our copper 2+ gains an electron and becomes copper 1+. That means that our copper 2+ ion, our actual copper chloride 2- ion, has been reduced. It's gained an electron. Now the question was actually, what is the role of the copper metal? Well, we know that reduction and oxidation must happen together, redox, and so if we're having this being reduced, our copper metal must have been oxidized. It must have been our reducing agent. And so in this case, we take our copper metal, and it becomes a copper plus ion plus an electron. So we had our complex ion being reduced, gaining an electron. Therefore, because reduction and oxidation must happen at the same time, we therefore have our copper metal being oxidized to the copper plus and an electron. And you can imagine sort of combining those two half equations and everything matches up here. We'd cancel out our one electron, and we'd essentially have the copper 2 plus our copper metal. Our electrons then cancel out. It's going to give us 2 lots of the copper plus 1 ion. So the copper metal is actually oxidized, acts as a reducing agent. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on our tuition website. I offer online tuition for chemistry, so check out those tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.